All right, eighth graders, this is your lesson 3.3 plate tectonics and landform notes. So you should be filling out your notes packet while you watch this video. The notes packet can be found online in Schoology by printing out the PDF, or you can get a copy from the teacher provided in class. So by the end of this lesson, you should be able to explain how forces from tectonic plates movement and relate processes deform Earth's crust and result in landforms. In other words, you're going to know how the plates move and how they destroy crust and how they make different land features. So what does the theory of plate tectonics explain? So again, that the Earth is divided in 5 physical layers, from the outermost layer to the center, and they are, starting from the outermost layer, the lithosphere, then you have the asthenosphere, the mesosphere, outer core, and then inner core. So then the lithosphere itself is divided into those large moving pieces called plates, tectonic plates. And then below the lithosphere, you have something called the asthenosphere. And this is where the slow moving rock makes the lithospheric plates move around. So in the asthenosphere, you have that process called convection currents going on, making the plates, which are in the lithosphere, move around. So the lithosphere is broken up into those 15 major tectonic plates that fit together like pieces of a jigsaw puzzle. We know it as Pangea. So these plates differ in size, shape, density, thickness, and composition. Tectonic plates may be composed of oceanic or continental lithosphere or both. So in other words, for instance, the North American plate, it's actually both part of the Atlantic Ocean and part of the North American continent. So it has both oceanic and continental lithosphere. Continental lithosphere is thicker, older, and less dense than oceanic lithosphere. Tectonic plates move slowly around Earth's surface and interact with one another. This causes the properties of tectonic plates to change over time. So in other words, these plates don't always stay the same size, nor they have the same features on top of it all the time. They are going to change over time. So we're going to talk about words like density. Okay, what does it mean for an object to be less dense? So here's an example. We call this a density column. So the reason why it's called a density column is the items that are more dense, meaning have more matter to them per unit of volume, are located toward the bottom. So for instance, this bolt is the most dense out of all of these liquids and all of these solids. And you can actually make one of these. This actually is truly makeable. It will turn out exactly the same way. So if you had all of these items and all these items and all these liquids, you actually could make this density column. Okay. So honey would be the most dense liquid, and then lamp oil, which used to put for burning oil lamps, actually is the least dense because it actually has the least amount of matter per unit of volume. And then you can actually float a ping pong ball on top of it, which kind of makes sense because a ping pong ball is hollow, doesn't have very much matter in it, so it'll float on top. And if you compare things like milk versus dish soap, milk is more dense than dish soap. So if you were to actually look at these, now this doesn't give you the physical look of these liquids. Here it gives you the actual density number. So if you were to actually put these in the right order, which liquid would be labeled as B in the density column? So here's B, it's second from the top. So it's going to be the second least dense, okay? Your answer should actually be the salt water, because canola oil is the least dense, then salt water would go here at B, then ether would go at C, and then corn syrup would go at D. So the higher the number of density means more dense. So you're going to hear this word called stress. Stress is related to the movement of plate tectonics. Tectonic plates shape Earth's surface by slowly forming and changing crustal features such as mountains. Tectonic plate movement puts stress on rock. Stress is the amount of force per area on a body. So for instance, right now, we're not talking about emotional stress, we're talking about physical stress. So you pushing down on your mouse, that's actually a form of stress, okay? It's the force that you push on an area. Deformation, the bending, tilting, and breaking of Earth's crust, the change in the shape of a rock in response to stress. So stress causes deformation. In other words, you're going to either break something, bend something, make it move or shift. So stress causes deformation. And there's three types of stresses that we're going to talk about. There's compression, tension, and shearing. So these are the three types of stresses. We're going to go through each one of these. The first one is compression. Okay, so as you can see, compression, I mean, if you drew an arrow, which I want you to draw an arrow going this direction and an arrow pointing like this. So they're going to be pushing toward each other. So this stress squeezes or shortens material. Compressions can cause fold. So if you look at this, the rock actually looks wavy. That's considered a fold. This occurs when two plates moving toward each other sometimes causes compression. So if you have one plate moving in, toward another plate, you're going to compress the two plates together. Folding occurs where Earth's lithosphere is less rigid, meaning less thick, more flexible, and rock that is less rigid bends instead of breaking. So compression can cause breaks in rocks or faults where Earth's lithosphere is more rigid. So if it's really, really thick or breakable, then you're going to make, instead of it folding, it's actually going to cause cracks when you have compression. A lot of times this happens in basement walls. You'll get compression in those areas because you've got your walls of your building or of your house pushing up against the rocks and soil. So your walls are very rigid, so therefore it's going to create cracks in the walls. The second type of stress is called tension. This is where the material actually is lengthened or is pulled apart. The way I would describe this is if you take your gum after you've chewed it for a while and take it out, or like silly putty, and pull it apart, it gets thinner in the middle and thicker on the ends. So this happens when two plates move away from one another, causing tension. Rocks under tension stretch and become thinner in the middle. When tension is great, then the strength of rock, it can deform the rock by breaking it. Faults form when rock breaks. So again, this is another way you can actually create cracks in the earth, also known as faults, when you have tension. Two plates are going away from each other. They're separating. The third one is shearing. And this stress causes material to twist or become distorted. It can occur when two tectonic plates move past each other. So one is going to go one direction and the other one is going to slide against the other. The rocks do not move smoothly. Instead, they grind against each other. You can kind of suspect what this is going to cause. Okay, this grinding, one plate going one direction, one plate going the other. So if you took a look at this mountain and I asked you which type of stress created this mountain, again, your choices would be compression, tension, or shearing. Remember, compression is when two plates move and run into each other. Tension is when two plates separate each other. And shearing is when two plates grind against each other. So with that being said, okay, if you look at this properly, you should notice that there are folds in it. So this is caused by compression, two plates running into each other. In fact, a lot of our mountains that you see actually are created by compression. They've got these like curvy features in the mountain. Take a look at this, okay? Here you've got a type of stress. Which stress would you actually consider would create this, an earthquake, okay? This is the before and this is after. I want you to notice that the difference in distances that this church bell is. Notice here the distance from this red building and the church tower. Then look at it after. The church tower is now closer to the red building. So which means the right side of this plate moved toward this guy, and then the left side maybe moved away from this guy if this guy was stationary. So this is our two plates grinding against each other. So the stress with this one would be shearing. So there are different types of plate boundaries that are associated with each type of stress. So deformation may occur throughout a tectonic plate. However, most deformation occurs at boundaries where tectonic plates meet. These plate boundaries may be on the ocean floor, around the edges of continents, or even within a continent. So there are going to be three types of plate boundaries that we're going to talk about. This actually is a review from your web quest that you did on plate boundaries. There are convergent boundaries, divergent boundaries, and transform boundaries. So if you look here, this is actually a map of the different plates, and it's hard to see because it's kind of fuzzy, but the arrows are going to show the different type of boundaries that occur. Okay, here you've got two plates that are going to run into each other. Those are called convergent. Here you've got two plates that are sliding past each other. Those are called transform. And then here you've got plates that are moving away from each other. These are called divergent. They're dividing the crust in half. So let's talk about the first type of boundary, and that's convergent boundaries. This is when the tectonic plates move toward each other. They either collide or converge boundaries. So whenever I think of this, I think of connecting or converging, colliding, anywhere to help you remember the word converge. So convergent boundaries is the boundary between tectonic plates that are colliding. Every boundary is associated with a type of stress. The stress associated with convergent boundaries is compression. Makes sense. It's compression with the C, convergent with the C. Easy way to remember that. These collisions involve different types of plates. The density of the plates helps determine what the plates will do. So this is where the word density is going to become important for us. So if a plate is more dense, what do you hypothesize is going to happen to that plate? Well, if you looked back to this density column that we had at the very beginning, if you have something that is more dense, where do you find it? The answer is toward the bottom. So if you have a plate that's more dense, what's going to happen to that plate? Well, it's going to sink toward the bottom. In this case, it's going to sink into the mantle. So if you have two oceanic plates, one of them is going to sink underneath the other. So when you have two oceanic plates, crust, that one is typically cooler and more dense, the denser plate sinks under the less dense plate. The process of one plate sinking below another is called subduction. So here, you're going to actually create volcanoes that are actually found in the middle of the ocean. These are how the Hawaiian Islands, this is how like the Pacific islands of the Philippines were created. Okay, the Pacific plate actually sinks underneath the Eurasian plate, creating these volcanic islands. So this particular type of boundary creates volcanoes specifically in the middle of the ocean, creating volcanic islands. Or you can have a oceanic crust sink against a continental crust. So instead of making the volcanoes in the middle of the ocean, you're going to make the volcanoes on land. So this is called a convergent boundary with oceanic and continental plates. So here, a convergent boundary occurs when an oceanic plate collides with a continental plate. So these are two different types of plates. Subduction still occurs here. Since the oceanic plate is more dense, it's going to sink beneath the continental plate. So again, you're going to make volcanoes in this case, but just on top of continental crust. So Mount St. Helens was created this way. So that's actually a great example. It's the Pacific Ocean. The Pacific oceanic plate sinks underneath the North American, which is a lithosphere, a continental plate. So those two run into each other and creating volcanoes on the coast of California and Washington State. You could also have two plates that are continental. Now these will actually meet at a convergent boundary and they'll push up against each other. So because neither is more dense than the other, instead they're going to buckle up. So this is going to create actual mountains. So Mount Everest, the Himalayan mountains, these were actually created this way when two plates run into each other and buckle up. I always imagine like two wrestlers that are of the same weight class and they run into each other and then they push up. That's how I remember this one. Okay, you're actually going to ignore this video clip. Okay, we're going to move on. So again, the features associated with convergent boundaries are mountains, volcanoes, and trenches go along with those subduction zones. Again, mountains, they're created by when two continental plates run into each other. The Appalachian Mountains were formed when North American plate collided with the Eurasian plate and African plates. That's why another piece of evidence that proves that those plates were once connected together at one point in time. You could have volcanoes. Again, this occurs when subduction occurs. You'll get the magma will sink into the lithosphere, forming forming a whole bunch of magma. I'm sorry, the crust will sink into the lithosphere, forming a whole bunch of magma, and that magma is going to build up and eventually create a volcano. So like I'd mentioned before, if it's to an oceanic plate and an oceanic plate, they're going to actually create what they call a volcanic arc and a volcanic island arc, and the Philippines are the great example of it. Sometimes if you had an oceanic plate sunk below a continental plate, you also might get a continental island arc. The Cascade Mountains in the Pacific Northwest are examples of that. Like I said, Mount St. Helens, they're part of the Cascade Mountains. So volcanic islands are created when you have two oceanic crests run into each other. An island arc is when you have an oceanic and a continental plate run into each other. And then trenches, those are formed when you have subduction areas. So the deepest trench that we know of is actually the Mariana Trench, which actually might be less up to date now, because I know that in China they just found another trench that might actually be deeper than the Mariana Trench. I just read this article on it yesterday. So this actually may now change. But for right now, you guys are going to learn that the Mariana Trench is our deepest trench. If you look here, the Mariana Trench, if you took Mount Everest, it would still not be the height of Mount Everest. In fact, the height of Mount Everest, if you were put it at the bottom of the ocean, is 29,000 feet. The Mariana Trench, as far as we can measure so far, is 36,000 feet. So it's a pretty darn deep trench. And we were able to measure it not because of being able to go down, it's because we use sonar and seismic waves and sonar waves. The second type of boundary is divergent, and this is where the plates actually separate from each other. They're going to divide. So the boundary between two tectonic plates are when they're moving away from each other. So think divergent, divide, separate. The stress associated with divergent boundaries is tension. Okay, again, they're moving away from each other. So the lithosphere is going to thin and become really, really thin and create a fault or a crack. The thinning allows the asthenosphere to rise toward the Earth's surface and melt. The melting produces magma, which moves to the Earth's surface where it cools and solidifies. This process forms new lithosphere at divergent boundaries. This should sound familiar. This is seafloor spreading. Even though new lithospheres form at divergent boundaries, it does not mean that the lithosphere is becoming bigger. Old lithosphere is destroyed in subduction zones at convergent boundaries where one plate sinks beneath another and eventually melts. So again, you should have remembered when we did this with seafloor spreading, you're going to have one arrow go this direction to the right and another arrow go this direction to the left. You'll have magma rising up. You'll have a rift valley where magma is cooling and hardening, becoming new crust. And on the sides here, you'll eventually get subduction so that the width of the oceanic floor isn't getting bigger. It's just being recycled. So again, faults are associated with divergent boundaries. Faults form when the rocks break. Along faults, pieces of lithosphere are called blocks, either drop down or lifted up. Blocks that drop down along faults can form valleys. Other blocks are lifted up. The blocks that are lifted up form fault block mountains, which appear on either side of a valley. So you can have divergent boundaries on land. The Grand Teton Mountains in western North America are an example of divergent boundaries that have occurred on continental crust, wherein this plate separated from each other, creating a fault, and then some of the crust fell down, creating fault block mountains. You'll have rifting, the process by which Earth's lithosphere pulls apart to form long, narrow, faulted rift valleys. And in rifting, you'll have rift zones. Rift zones are areas with many long, deep cracks in the Earth's lithosphere. Again, it's where magma rises up through these cracks to form volcanic mountains and tall, flat-topped plateaus. On the ocean floor, rifting forms mid-ocean ridges, and at mid-ocean ridges, magma rises through the cracks in the oceanic lithosphere, forming volcanic mountains. Again, this is where seafloor spreading occurs. Last boundary is the transform boundary. And this one's pretty easy because you can tell on this, these are the two plates that are going to slide past each other. So you're going to have one arrow going up diagonally and one arrow going down diagonally in these white boxes that you need to write in your notes. So two tectonic plates can move past one another in opposite directions to form a transform boundary. The transform boundary, the boundary between two tectonic plates that are sliding past each other horizontally. So they're not going to go up and down, they're going to go side to side. And the stress associated with this one is shearing. Okay, and in this case, they don't move smoothly. In fact, they actually have like a burst of energy and they just shift suddenly. Hence, you're going to have rocks that break, and this is where your earthquakes occur. So here you can see, again, you can have major and minor earthquakes associated with transform boundaries. On the ocean floor, transform boundaries can occur, and you'll get mid-ocean ridges. So here you can see this. If this was a river, you could see how the river was cut off because one plate went to the right, which is the top one. So you'll draw an arrow going to the right in the white box at the top, and then you'll draw an arrow to the left in the second white box at the bottom. Signs of transform boundaries include offset streams and fences. So, skipping over, Hawaiian Islands are a little different. The volcanoes of the Hawaiian Islands are a little different. So, in this case, volcanic landforms occur away from plate boundaries. Some chains of volcanic islands, such as the Hawaiian Islands, form far from tectonic plate boundaries. So the volcanic islands are a little different of Hawaii. These are actually made not by plate boundaries, they're made by places called hotspots. At a hotspot, magma rises from deep within the earth through the lithosphere to reach the ocean floor. On the ocean floor, repeated lava flows build up to form an undersea volcano. Over time, the top of the volcano reaches the ocean surface and a volcanic island forms. As the oceanic plate moves, new oceanic lithosphere is positioned over the hotspot. A volcanic island may eventually form, with the oldest islands in an island chain that are farthest from the hotspot, and the newest island is closest to the hotspot. So here you have a picture of a hotspot. What's going to end up happening is the plate is going to move over this hotspot. The island that's over the hotspot, that volcano, is going to be the newest volcano, the newest volcanic island. The island that's furthest away from the hotspot is actually going to be the oldest volcanic island. Okay, so you're going to watch a YouTube next in the video and watch the volcano islands being formed there, and then you're going to continue watching it with me, giving you some commentary over the video. So go ahead and start watching the video next.
Volcanoes usually occur at plate boundaries, where the continents collide. When they hit, they release unimaginable energy, punching up molten rock from deep inside the Earth. The Pacific Ring of Fire marks a whole series of these plate edges. It's got half the world's active volcanoes. Hawaii is more than 2,000 miles from the nearest collision zone. Beneath the ocean floor is a mysterious area of super-hot liquid rock. Hot enough to melt a hole through the Pacific plate, punching up fresh lava. It's called a hot spot. The ocean floor is creeping gradually northwest at 3 inches a year, but the hot spot under it doesn't move. A volcanic island builds up, but as it moves away from the hot spot, it is cut off from the source of lava and dies. Over the hot spot, a new volcano forms. But if the big island is growing, then what's happening to the island of Oahu? Oahu should be shield-shaped, circular, but it's not. It's long and thin. There's a chunk of it missing. All that's left are 1,000-foot-high cliffs.
Because you can obviously tell that this isn't a shield volcano anymore, that there's something definitely missing from the spot.
As the water turns the rock to soil, the cracks burrow even deeper. A fatal weak spot develops, until one day, it all just lets go. This cliff is a crack, 1,000 feet deep. Based on the shape of Oahu and the height of the cliffs, Lloyd estimates the land used to extend out from here for another 20 miles.
All this used to be solid rock. And all that rock disappeared to the ocean below.
Two million years ago, the island fell apart. 300 square miles, 20 trillion tons of rock dumped in the Pacific Ocean. That's why Oahu has an unusual shape. The rock slide really has taken a bite out of the island.
So this is actually a really good video. It's one of my favorites when it comes to explaining how the Hawaiian hotspot and relating it to plate boundaries. So as you watch this video here, you have an example of how two crusts, if you can guess, this one is going to be, this can be oceanic and continental, or it can be continental and oceanic, as they run into each other. Here you'll have subduction, and this would be the trench. You'll have the one plate sinking underneath the other, and that magma that flows and builds underneath in the mantle is going to rise up and form these mountains. And a lot of these mountains are found along this area here. This would be the Pacific Ocean, and these are all volcanoes that are occurring around the Pacific plate. And we call this area specifically the Ring of Fire. Makes sense considering you have a whole bunch of volcanoes forming in this area. So literally it's this oceanic plate sinking underneath this continental plate. So, but Hawaii is found not along this plate boundary. It's actually found in the middle of a plate. So that's why Hawaii is made a little differently. It's made on a hot spot. So again, it actually starts with magma rising up through the ocean floor and then contacting water and cooling and hardening. So that's what you see here. This is actually live footage, and you can actually visit Hawaii and see this actually happening. You don't get too close to it. But here is an example of how this works. So this plate is moving, but the hotspot doesn't go anywhere. So as you can tell, new volcanoes are being made as this plate moves around. Now, keep in mind, this movement's very, very slow. I mean, we're talking like slow, 2.5 centimeters per year. So it's not like all of a sudden we're going to pop, there's a volcano. This is going to happen over time. Mount Kilauea is currently being made right now. In fact, that volcano is constantly exploding. That's because that part of the plate is sitting on top of the hot spot right now. So if you keep going with this video, okay, again, this is kind of like a fast forward motion of how a Hawaiian island or a volcanic island would form. So if I were to actually label these, like if there was a volcano here up in the upper left-hand corner, and then another volcano here kind of in the middle, and then a third volcano here, 1, 2, 3, in your head, you should ask yourself which volcano is going to be the oldest. What should be this first one over here, because it's the furthest away from the hot spot. The volcano over here that's closest to the hot spot is going to be the newest because it's on top of the, or nearest to the hot spot. So again, this plate keeps moving over the hot spot, making more of these volcanic islands. So hence you get the volcanic islands of Hawaii. Okay. So now you're pretty much done with these notes, and you're probably moving forward to working on your study guide and some of the projects that I've signed for you. So please play this video back at any time if you need to review anything about plate tectonics, about plate boundaries, stresses, and hot spots. All right.